Hello, Prof. Joe here. Today we're going to talk about relative motion, and we're going to see how the concept of relative motion can help us take a complex general planar motion problem and break it down into two simpler problems that we already know how to solve. So let's see how we can do that. Okay, to do that, I want you to take a look at this video. We have Katrina Young, a local Olympian from Shoreline, Washington, doing a dive. And as you can see, as an Earth-fixed observer, which is what the camera is, you can see general planar motion. We have translation and rotation going on. However, picture yourself as Katrina. What do you feel? Well, obviously you know you're falling, but probably what you feel mostly is the spinning. You're just doing a bunch of spins and twists. Okay? You're doing pure rotation about your local coordinate system. What we want to do today is to see if we can mathematically separate those two and solve a general planar motion problem as a combination of translation and rotation. And to do that, we're going to use this ruler. We're in 2D right now, so we're going to picture just 2D motion. And I have this ruler. Picture it as it flies through the air and rotates. Okay, we have a ruler that's flying through the air and rotating. And I'm just going to pick 2 points in time and trace those on the board. So one point in time, let's just say it's here. Okay, and then it translates and rotates until it's here. And for that change, we have a certain time. We'll just call it delta t. And now I want to label the ends. I'm going to call this end A, and I'm going to call this end over here B. And A and B are still part of this ruler. We got A over here. We got B over here. And then I want to use some vectors to show the change in position. For A, we would have this vector, and that would be our delta. Or delta means change in the position of A. Same thing for B. That's going to be our change in position of B. Now, hopefully you can see that the vectors are different in both direction and magnitude. So what we want to do is see if we can come up with a relationship between these vectors. And the way that we're going to do it is a thought experiment. Picture the same ruler, only translating over the same delta t. Let's just take out the rotation. Okay, so we have the same ruler. It's right here. And instead of rotating and translating, we're just going to picture the same delta t. What happens if it just translates? Okay, I'll put it right here. It only translated, did not rotate, and we got ourselves another ruler. OK, now that ruler, through the same time, translated the same distance as RA. We're picking RA as what we call our local coordinate axis system. Okay, and I'm going to write that on here. I'm going to have my x prime, my y prime, which would be my local coordinate system axes. And of course, I have an Earth-fixed coordinate system, which we can draw pretty much wherever we want, and call it x and y. It's very important that our x and our x prime line up and our y prime line up, because that allows us to use the same i's and j's in our equations. OK, so now what we're going to do is we're going to go ahead and label another point. I'm going to call this point B prime. This isn't the real B. This is our imaginary B on an imaginary ruler that only translated. But the question we can ask ourselves is, what's the vector that shows the motion from B to B prime? Hopefully you can see it would be delta RA, because if you're only translating, all the points on an object move the same. So I can draw that right here, and that is my delta RA. OK, so my change in RA, I have two vectors up here, my change in RA, change in RB. What if I just add another one? I'll add another mystery vector and make a triangle. Okay. Well, this mystery vector is really showing us how B changes in relationship to A, right? If you were traveling along A and this is your Earth fixed coordinate, or this is your local coordinate system, x prime and y prime, how B changes within that coordinate system is what this third vector is. So we're going to name it just like we did in relative motion. That's going to be our change in the position of B with respect to A. Okay? If we're putting ourselves on the local coordinate system, this is how B is changing in our reference point. Just as Katrina, as she dives down, well, in her reference point, she's just spinning. And hopefully you can see here, the reference point of A, B is just spinning about it, as if it was pure rotation. Okay. So let's do our tip-to-tail relationship on these three vectors. We have the change in position of A plus the change in position of B with respect to A equals the change in position of B. And I got to make sure I got my harpoons because this is a vector relationship, tip-to-tail relationship. And this all happened over some given delta t. I can divide both sides of the equation by delta t. And as I imagine the delta t gets shorter and shorter and shorter till it's infinitesimally small, the limit as this approaches 0 would be the rate of change of the position of A with respect to time plus the rate of change of the position of B with respect to A with respect to time is going to be equal to the rate of change of B with respect to time. OK. And one more step. What is the rate of change of the position of A with respect to time? Well, that's the velocity of A as a vector plus the velocity of B with respect to A is equal to the velocity of B. This should look very familiar because this is the same as our relative motion equation that we derived in particle kinematics. You can see the same pseudo-canceling. If I picture this A is on top and this A is on bottom, you can see those two cancel out and we're left with our B. We got to make sure that relationship always stands. And I'm just going to rearrange it to make it look just like what we used in relative motion before. OK, now what we've learned here is actually really helpful. It's telling us that in general planar motion on a rigid body, we can find the velocity of one point on that body based off the velocity of any other point on that body. We choose a point, we put our local coordinate system, and then we can find the velocity of another point if we know the relative velocity of the two. Now, in this particular problem, this is a rigid body, and those 2 points are not getting any further or any closer away from each other. They're the two endpoints. There's no distance changing or what I call sliding. So since there's no distance changing, hopefully you can picture 2A, it looks like B is just spinning around it. So we actually have pure rotation in this second term. The second term, the velocity of B with respect to A, would be pure rotation. And what did we learn in pure rotation? We learned that the translational velocity within that local coordinate system is going to be equal to rotational velocity crossed with position. In other words, the velocity of B is equal to the velocity of A plus omega of that body crossed with the position of B with respect to A. A couple of really important things in this equation. Each rigid body is going to have its own omega. That's why I like to always label my omegas. This is going to be the omega of our object AB. Look at the subscript of our position vector. It matches the subscript of our velocity vector, and our pseudo-canceling hasn't gone away. I have an A over here and an A over here that would cancel out to give me the B. And what we have here is our relative motion equation for velocity that allows us to find the velocity of any point on a rigid body undergoing general planar motion based off the velocity of another point and the omega. Let's go ahead and use this in an example problem. OK, we have an example problem here. This is a fundamental problem from the Hibbler text. It says crank OA rotates with a constant angular velocity of omega equals 12 radians per second. Let's start our givens. Omega, and I always want to label it. It's telling me this is OA, so omega OA is equal to 12 radians per second. Find the velocity. Well, we label our finds here. We're supposed to find the velocity of B and omega, the angular velocity of the rod AB. I'll call that omega AB. That's what we're supposed to find. So each rigid body is going to have its own rotation. And let's see if I can make this a little bigger. OK, so we're looking at rod AB, and we want to find out what's the velocity of B. Well, we've got a mechanism here that has dependencies, right? A is rigidly connected to AB. A is only one point. It has to be traveling the same velocity regardless of which of those two links we look at. Okay? So we can figure out the velocity of A. And if we know the velocity of A, we can figure out the velocity of B based on that velocity. How? Using relative motion, right? Velocity of B is going to be equal to the velocity of A plus omega AB crossed with the position of B with respect to A. And of course, I'm making sure I have my omega labeled properly and my pseudo-canceling works with the subscripts. Okay? So that's going to be my governing equation for this problem. So let's start trying to fill it out. We don't know any of these yet, but the velocity of A, we have some hints. What I'm going to do is I'm going to break this assembly apart. And for now, to make my life simpler, just look at my OA. So I have my OA, where I have O is down here, and it's rotating about O. This is fixed to the Earth. So we know this is pure rotation. Point A is rotating about O, and we would expect its velocity to be going that way. Okay. We are given the omega, and we know that there's a relationship between translational and rotational velocity. I'm going to use the scalar relationship and then use my picture to get the direction so I can have the full vector. You could use the cross product directly and get the same answer. So I'm going to say my velocity of A, looking at this picture I just drew, is going to be equal to omega OA times the radius, which is 0.3 meters. And that's going to be the radius of A with respect to O. Put those two together. OA is 12 radians per second. ROA is 0.3 meters. And we know then that VA's magnitude is going to be 3.6 meters per second. Okay, but we want VA as a vector so it can go in our equation. So I already drew it. I know which direction it's going in. I need a coordinate system. And I'm going to use my typical XY rectangular coordinate system. And so that's going to make my VA in the negative x direction, or negative I. So VA as a vector is going to be equal to negative 3.6 meters per second I. OK, I've got one. The next one, omega AB. What do we know about that? Initially, you might think we don't know anything about it, but you'd be wrong. A lot of students overlook a really important point. We know the direction of omega AB. How do we know that? Well, look at the picture. If we look at the picture, we know as A is rotating that way, OA would tend to rotate in this direction, which with our right hand gives us a positive. Yes, this is my right hand. I know the image is flipped. It gives us a positive direction in the K. But you know, we don't even need to know the sense. We don't even need to know if it's positive or negative. We just need to know that it's in the K. It has to be in the K because we're in general planar motion. So we write down omega AB as a vector is equal to the magnitude of it, whatever that is, in the K. This is a really powerful tool. Do not forget about that, given that we know omega AB is in the K direction. OK, we got something about that one. And last one, the position of B with respect to A. I'm going to draw that second link. Let me just get rid of the picture here. This is A, this is B, this is 0.6 meters, and this is 30 degrees. OK, so we need the position of B with respect to A. That means that you're standing at A walking to B, right? The position of B with respect to A. If I'm here at A and I'm walking to B, I'm only allowed to go in two directions, X and Y. So I'd first go down in the Y direction, and then I walk over in the X direction. And I have a triangle, and I bet you can guess the sides. 0.6 cosine of 30, 0.6 sine of 30. And we can write that as a vector. The position of B with respect to A as a vector is going to be equal to, I'm going to do my i's first, positive I, 0.6 cosine 30 degrees in the I, and negative j, 0.6 sine of 30 degrees in the j direction. Okay, I've got all three signs of all three vectors in my equation. I do know one more thing. What do I know about VB? Well, if I bring the picture back up, you can see that VB is constrained. It is a piston traveling in that slot, and it can only go up and down. So what do we know about it? We know there's no I component. It has to be in the j direction. We know there's no k component. This is planar motion. So let's write that down too. We know that VB as a vector is going to be whatever its magnitude is in the j. I like to keep my negative signs in my variable so that later when I solve for it, I know that there's a negative there and I don't forget I put it in before. But I'm still going to look at my drawing and say, well, if A is going that direction, I'd expect B to be going up, so I expect my VB to be positive. If I get a negative, I made a mistake. It's good to have those checks as you're doing your work. OK, now that I have all four of these, let's go ahead and plug it in and see if we can solve. VBJ equals VA, which is negative 3.6 I, plus omega AB, which is our magnitude in the k direction, crossed with 0.6 times the cosine of 30 I minus 0.6 times the sine of 30 j, and all of that is going to be in meters per second. OK, now we just need to perform the cross product. Many of you probably have experience doing the cross product as a pseudo-determinant, and that's a great way to do it, and that'll work great in this problem. However, there is a shortcut that you can use as well. When you're using the shortcut, I always recommend writing this little key up. You just write I, j, and k, and you write a circle that's going counterclockwise. Okay? This is a reminder to tell us when to use negatives and also tell us what we expect to get. And how it works is, well, I'll show you. We got VBJ equals negative 3.6 I. Let's perform this cross product. The first one, I'm going to be doing a k crossed with an I. A k crossed with an I, you can see it goes in the direction of this arrow. K crossed with I gives me a positive j. And since neither of these have a negative on them, I expect positive. So I'd say plus 0.6 omega AB cosine of 30 degrees. And it's k crossed I, so I get j. OK, the next one is k crossed with j. K crossed with j goes in the opposite direction of the arrow, so I have to add a negative sign. I also have a negative sign right here. Two negatives make a positive, so I'd have plus 0.6 omega AB times the sine of 30 degrees. And it's a k crossed with a j, so I get an I. Great. We have our equation. And how many unknowns do we have? Well, we have VB, and we have omega AB. And how many equations do we have? This is kind of a tricky question. Initially, you might say 1, but this is a vector equation, remember. So this vector equation has i's and j's in it. So we actually have 2 equations, and we can solve. Let's write the i's first, and then we'll write the j's. On the left-hand side, there's no i's, so we say 0 equals all of the i's, negative 3.6. I'm going to leave the i's out because I'm now converting to a scalar equation. In order to do that, I like to give myself a little reminder. That's my direction for this entire line. That little reminder helps me remember that I removed the direction. I'm now in scalar form. 0 is equal to negative 3.6. This one's a j, so I leave it out, plus 0.6 omega AB times the sine of 30. OK, only one unknown in that equation, so we can go ahead and solve for it. we would end up with 3.6 equals 0.6 times the sine of 30 degrees times omega AB. And we can solve for omega AB. And that gives us 12. And the units, I'm going to have meters per second on the top, meters on the bottom. So that's going to be nothing per second or radians per second, because radians is our non-unit. Now, I do want to point out that 12 is the same as the given omega. That is a coincidence because this is half, and we have a 30 in here, and our sine of 30 is half. And that's what's happening. That's not, it's just for this one snapshot. If I were to change the angle or change either of those magnitudes, those two would not have been equal to each other. So we have our omega AB. And now we just need to solve for our velocity of B. I'm going to give myself some room, and we'll do that. OK, we got a little bit more room now. You can see I just copied our vector equation up here, and the x direction that we used to solve for our omega. And now we're going to do the y direction. And we have VB on one side. And on the other side, we only have one j component, which is 0.6 omega AB times the cosine of 30 degrees. So our VB is going to be equal to 0.6 times our 12, which we solved for, times the cosine of 30 degrees. And we get 6.235 meters per second, or for your homework, 6.24 meters per second. OK, we solve for the two things we need to solve for. We're going to do a quick check and make sure they make sense. I expected a positive omega AB, and I got that. My positive omega AB is telling me it's rotating, as my right hand shows, which is what I expected. I also have a positive VB, which would mean, well, VB is in the positive j, so that's going up. And I think if I look at my original picture, if this rod is going this way, we expect B to be going up. It's always good to make sure your answer makes sense. Great. Let me know if you have any questions.